Good afternoon, everyone. I'm Jia Yin from Scalable Solvers Group, and today I'm happy to share our work on dynamic mode decomposition of one-time dynamics for non-equilibrium Green's function. This problem originates from quantum many-body systems. For quantum, that means the particles are very small, and for many-body, that means we have a large number of particles. There are many applications of quantum many-body systems. For example, in quantum chemistry, where for each molecule we have one nuclei and surrounded by many electrons. In Bose-Einstein condensate, where we have a large number of identical particles called bosons. And in condensed matter, for example, graphene and graphite, where we have a large number of atoms stacking together. So studying the quantum many-body systems can help us understand the structures and the properties of these systems. But simulating quantum many-body systems is very expensive. The dynamics of such a system can be described by the Schrödinger equation as given here, but one problem is the dimension of the wave function psi grows exponentially with the number of particles, as it can be expressed as the tensor product of each single particle wave function. And another problem is, here is the exact solution of the Schrödinger equation, but the exponential operator of the Hamiltonian is difficult to compute. And as this Hamiltonian is time-dependent, we need to act a time-ordering operator on this exponential operator, which makes it even more difficult to compute. So our aim is to simplify the system and reduce the computational cost. One possible way is through the perturbation theory, where we can simplify the many-body system and represent it by a single particle Green's function. In this case, we no longer need to take care of all the particles. Instead, we can focus on one single particle. And the interactions between this particle and the remaining particles can be summarized into one term called the self-energy. The non-equilibrium Green's function can be expressed by gt t prime, where t and t prime are two time arguments. From the Green's function, we can get the estimations of some interesting physical observables, including the occupation number and the band structure. The occupation number describes the distribution of the particles among different sites. And from the evolution of this number, we can get how the system evolves under certain perturbations. This can help us understand the structure and the properties of the system. From the band structure, we can get to know the energy states of the system, and it can help us gain knowledge about the electronic properties of the system. But although we have simplified the system and used a single particle Green's function to represent it, it is still very difficult to get the values for the Green's function. Actually, the equation of motion for the Green's function can be expressed by a set of coupled integral differential equations, which are difficult to solve. And one of the equations is given here as an example. In this integral term, we notice that the self-energy sigma is dependent on the Green's function, so that this term is a nonlinear term, which introduces more difficulty in designing the numerical schemes. And as this Green's function is a two-time function, as shown in this figure, in order to evolve from capital T one time forward to capital T plus delta T, we need to evolve both in the T direction and in the T prime direction. This introduces more complexity in this problem. So for a traditional numerical scheme, the computational cost is at order T cubed, and the memory cost is at order T squared. They both grow rapidly with the increase of the time T, so it is hard for us to evolve the system for a very long time. So we want to further reduce these two costs in order to evolve the system for a longer time. So we notice that for some physical observables, there is only one-time dynamics instead of the two-time dynamics of the Green's function. So instead of looking at the original equation for the Green's function, we can focus on the equation of motion for the one-time dynamics of the observable, for example, for the occupation number. The problem is the right-hand side of this equation, this f, is unknown, and it is hard to derive from the original equation. We can only implicitly get the value of f, and we do not know the explicit form of f. In this case, it is hard for us to design a numerical scheme to solve this equation of motion. Instead, we can use a data-driven method to predict the long-time dynamics from the data in a small time window. The idea is that We can solve the original equation for the Green's function in a small time window from t equals to 0 to t equals to 2, as shown in this red shaded region. After that, we can use the data in this region to construct a reduced order model for the dynamics of rho t, and use that model to extrapolate a long-time dynamics of this rho t. The specific data-driven method we use here is called the dynamic mode decomposition, and in short, it is DMD. As mentioned in the previous slide, we first solve the equation in a small time window, and then we can use DMD to construct a reduced order model for it. It is represented by this formula. It is the summation of R elements. In each term, the phi is a spatial mode, which describes the distribution of the oscillation frequency at different sites. The omega L is the frequency, and the coefficient is given by BL. DMD can give us these three terms simultaneously, and then we can construct the model for rho t. In order to get the estimation of rho t at a longer time, for example, t equals to 6, we just need to replace the t in this representation by t equals to 6, then we can get the value of rho t. So the idea is when t is smaller than or equal to tm, for example here, tm equals to 2, we numerically solve the original equation, and for larger t, we can predict the dynamics by this model. This slide summarizes the procedure for DMD. We first collect the data in a small time window, and then construct two data matrices, x1 and x2, as shown in this figure. They deviate by a one-time step delta t. Then we want to find out a matrix A such that x2 can be approximated by A times x1, and we believe that this matrix A contains all the major properties of the dynamics. From the eigen decomposition of A, we can get the spatial mode and the frequency, and it is easy to compute the coefficients. Finally, we can get the DMD approximation given by this formula. It is easy to see that both the computational cost and the memory cost is at order t, so the computational cost is reduced from order t cubed to order t, and the memory cost is reduced from order t squared to order t. In this case, we can evolve this system for a longer time. As an example, we consider a system with this Hamiltonian, where H0 is a stable system Hamiltonian, and HEST is a time-dependent external field, which is represented by this one, and ET is a pulse centered at t equals to 0.5 with the intensity given by I. In the weak field limit, that is when I goes to 0, there is some analysis saying that the dynamics of rho can be given by the Bess-Salpeter equation. So we can use the solution from this equation to compare with our DMD results, both the spatial modes and the frequencies, to see if they are reasonable. Here, the Green's function is given by gktt prime, and k represents the spatial discretization. We take a very small I equals to 0.001, and on the left-hand side, we show the DMD modes. On the right-hand side, we show the BSE eigenvectors. We can see that they're almost identical. We also compare the DMD frequencies with the BSE eigenvalues. They are also very similar. So DMD actually captures both the spatial and the temporal properties of the dynamics. We also compare the DMD extrapolation with a more intuitive extrapolation from discrete Fourier transform, and the results are shown in the left figure. Actually, the rho DMD matches well with the original trajectory, but the rho DFT deviates a lot from it, especially outside the sample window. So in our example, DFT extrapolation does not perform so well as DMD extrapolation. We also introduce a value C, which ranges from 0 to 1, and a value close to 1 represents a good extrapolation of the original trajectory. We plot the C values for both DMD and DFT for different cases. We can see that CDMD is always larger than CDFT, which means that for different spatial points, DMD always perform better than DFT extrapolation. The last observation is that the DMD can reconstruct and predict the trajectories well, even with only a few snapshots. Here, the time step is 0.1, and we take about 70 snapshots. But we can see that there is not even a complete wave inside the sampled window, but we can already use DMD to do a very good extrapolation until a very long time, like t equals to 200. When we choose a larger I equals to 1.5, we still take about 70 snapshots. Although the dynamics outside the sample window is very different from the dynamics inside the sample window, DMD can still give us a very good extrapolation. Oh, here are the summaries of my talk. We use DMD as a model order reduction technique to simulate the one-time dynamics from the non-equilibrium Green's function. And the advantage of it is that it can capture the spatial and temporal properties simultaneously. DMD reduces both the memory and computational costs to order t so that we can evolve the system for a longer time. And in our model problem, DMD outperforms DFT extrapolation. So this is all for my talk. Thank you very much. And I'm happy to take questions.
Thank you for the nice talk. Any questions?
So when the trajectory is very different outside the window that you choose at the beginning, do you need to increase the size of the window for that, or can it still be small?
I think this is problem dependent. Like in our problem, because there is a discretization in space. So when we collect the trajectories, actually we have the values at different k points actually, so that they can interact together, and we can get such a good extrapolation. But in some cases, when the dynamics are very different, we may need to increase the time sample window.
Okay, thanks.
Right. Any more questions? I have one question. Sorry, if just one small. Do you have any estimate of how the error scales with time? Error meaning with your the result with your DMD approximation and from the, let's say, the exact results. How do they? I mean, do the error get worse if you want to go to bigger, longer time?
Yeah, sometimes it will get worse, but in our problem, in this specific problem, there is no much difference when time gets longer.
Thanks.
Thank you.
So let's thank our speaker.